So today we're going to look at 109, Interest Applications. Compound interest allows interest to now earn interest year after year or compound after compound. In the old days, people actually had to sit down with simple adding machines and compute the interest that people earned in savings accounts. So compound interest was performed annually. But later on, with better calculators, banks started attracting business by offering interest compounded quarterly or monthly. Discrete calculations like this can be performed by dividing the interest rate by the number of times it's compounded annually, and then multiplying the exponent by n. So in other words, we give you less interest for a shorter time period, but we compound it more times. So the formula below can be adjusted to accommodate this method of compounding. I usually use this formula over here on the left, but it means the same as this formula over here. So this part's the same. A just stands for amount in the account after so many years, the future value, and P is the initial principal. It's the present value. So whether you call it future value, present value, or initial principal and then amount in the account, it's the same formula. So as you look through this, you're going to put your principal here, so that's what money you're investing, and then you're going to do 1 plus. This 1 is basically giving you your money back. So if you invest $2,000, you need your $2,000 back. Then you're going to take your interest rate that's expressed as a decimal, like 5% is 0.05, and you're going to divide it by n. So if n is just annually, then it's just 1. But if n is monthly, you're going to take your interest rate and divide it by 12 months in a year, or divide it by 4 if there's 4 quarters in the year. And then you compound it. So if n is just annually, t is your number of years. So if it was like 4 years, 1 times 4 is 4. So 4 times annually, you would just do 4 compounds. But if n is 12, you've divided your interest rate by 12 months. In 4 years, you would actually have 48 compounds. 12 times 4 is 48 compounds. The more times you compound something, the greater the interest accumulated is going to be, because you're gaining interest on interest. So let's look at a few of these. So if you invest $4,500 at an annual interest rate of 5%, find which balance is the largest. Do you want to compound annually for 3 years or quarterly for 4 years? Let's see what the difference would be. So 4,500 times 1 plus, so the interest rate is 5%, so 0.05 divided by, these are both, let's say, compounded annually, right? So divided by 1. And I'm raising it to the 1 times 3, which is just 3. So be very careful. You want to try this typing it into your own calculator. 4,500 times 1 plus 0.05 raised to the 3rd power. So you should get 5209 and 31 cents. 5209 and 31 cents. That's hard to read. 5209 and 31 cents. There we go. All right, so now what if it's quarterly and for 4 years? I guess I should have switched these, huh? Obviously 4 years is going to be better. So I gave quarterly and 4 years, so those are both better. So 4,500, 1 plus 0.05. To do quarterly, I divide my interest by 4 quarters, and then I make up for it up here in the exponent. 4 times 4 is going to be 16 compounds up here. 4,500 times 1 plus 0.05 divided by 4 raised to the 16th. So please make sure that you can type it into your own calculator and get the correct amount. If not, maybe I can help you troubleshoot what you're doing wrong. It probably involves parentheses. So I got 54.89 and 50 cents. So obviously that is the higher amount. And I should have I should have done this one quarterly for 3 and this one annually for 4, so I could really compare the difference. But that's all right, we just calculated it. All right, so how about this one? $10,000 is invested in an annual interest rate of 3.5%. Find which balance is largest. So do I want to do 6 years compounded 6 times per year or 5.5 years compounded monthly? Now they both have a fair shot, right? This one is for longer, but this one has more compounds. So let's evaluate this. So 10,000 times 1 plus, so the interest rate here is 3.5%. So 0.035 divided by 6, because it's 6 times per year, for 6 years. So 6 times 6 in the exponent is going to be 36 compounds. So we'll try this on our calculator. Try it yourself on your own calculator to make sure you know how to type it in correctly. I get $12,329.26. So this is how I typed mine in. 10,001 plus 0.035 divided by 6 raised to the 36th power. Part B, 10,000 again. 1 plus, still 3.5%. This time I'm dividing it by 12 months. And this is going to be 12 times 5.5 in my exponent. 10,000. 1 plus 0.035 divided by 12 raised to the 12 times 5.5. Came out pretty close, 12,119 and 37 cents. So it looks like the longer duration, 6 years, ended up beating out the 12 months per year of compounding. So now you should pause the video and try these 2 problems on your own. So pause the video now because I'm just going to put my answer up. Pause the video, try number 3 on your own to make sure you know how to do these interest problems. So the answers I got were 14,257.61, and the winner was B, 14,326.86. I don't know if it helps you to see how I typed it in on my calculator, but here's A, here's B, and my 2 answers. All right, so now what happens if I know how much I want to have in the account, but I'm not sure how much to start with? So Donovan is offered a $50,000 signing bonus in 4 years when he graduates from college. If the company that wants to hire him is expecting to earn 4% annually on its money, how much would the company need to invest now in order to pay Donovan the bonus in 4 years? They need $50,000. So $50,000 is going on this side. We don't know the present value. And then we can put in all the rest. Times 1 plus 0.04% annually and 4 years, right? 4 times 1 is 4. So this is actually just a number right here, this 1 plus 0.04 raised to the 4th power. So what you're going to want to do is come up with a number for that. 1 plus 0.04 raised to the 4th power. So that's kind of a lot of decimals. So if that was the number, 1.169, I'm just going to write ... How would I solve for the present value? I would divide the other side by 1.169 ... right, to get it to the other side. Wouldn't that get present value by itself? So in my calculator, take 50,000 divided by second answer. So the answer is above this negative key. So 50,000 divided by my answer. So they would have to invest $42,740 and 21 cents. If they put that much money away because they know they're giving him the bonus, then they kind of they save like $7,000 that they don't have to come up with because it's come up in interest for those 4 years while he's at college. All right, so here's the last interest formula. And if you had to do a problem like this on a test, I would give you this formula right here without this information, but this formula, you know how to use the different parts, and this formula. So A equals PE to the RT. So it says, notice that our continuous compounding formula looks a lot like the formula above. Without going through the derivation at this point, you should be able to begin to see how E ends up in the formula for continuous compounding. Because remember, E was the limit as n went to infinity, right, of this expression. 1 plus 1 over n to the nth, that is very similar to our compound interest. So if you're compounding continuously, we've put in 12 for n monthly. We could put in daily, 365. But what if we want to put in every second or every nanosecond? Wouldn't n approach infinity? So isn't that E? So this idea of n approaching infinity, see how you don't have E over here anymore? It's continuously compounding. So E is representing that we're continuously compounding. So if we deposit $4,000 at an interest rate of 6% compounded continuously, we do P, so 4,000 times E, which is a number, 2.7, remember, raised to the interest rate, which is 0.06, times T is 1 year. So on your calculator, 4,000. E to the x is right here. It's in blue above that natural log button. So second e to the x, 0.06 times 1, so 0.06. So we would have 42.47, 42.47, and 35 cents. So 42.47 and 35 cents. How about after 10 years? So we would do 4,000 e to the 0.06 times 10 instead. So I can go second entry, which is above the word enter, get what I had back. I just want to take 0.06 and multiply by 10. So 72.88 and 48 cents. So I'd have $7,288. So I haven't quite doubled my money yet, but you'll see some questions where I ask you to double your money. All right, so why don't you pause the video and try 6 and 7, and then you can check your answers in a minute. So now you're checking your answers. So you deposit $2,000 at an annual interest rate of 9.5% compounded continuously. How much do you have after 1 year? And then this should just be part B. How much do you have after 1 year to compare it with annually? So after 1 year, you have P times E to the R times T. 2,000 E to the 0.095. 2,000 E to the 0.095. 21.99. I hope that you've tried these on your own calculator. If not, please do the last one on your own calculator to make sure you don't have questions. All right, compounded annually. Okay, so I think I'm going to leave you to do B. So I know that you have to do B on your own. You're doing the same problem, but annually. So you're using the formula on the front page. And I'd like you to do 7 on your own so that I know that you put some thought into this today. So kind of like we did up here, except on this one you might have to do a little bit of guess and check. So set up your equation. You know it's 4% continuously compounded, 10 years, needs to be 150,000 in the account. How much is the principal? So you can either guess and check or use a similar strategy to what we did up in number 4. So you're going to take a picture of just the back page of 109 so that I can see your answers to 6 and 7 clearly and submit that using the link in Google Classroom.